Yes, thank you, Diego, for the introduction, and thank you to all the organizers for the opportunity to speak in this very nice conference. So today I will discuss an ongoing work with my PhD advisor, Luis Caffarelli, and it is about the construction and the analysis of an intermediate family of operators that are between the fractional Laplacian and a nonlocal Monge-Ampere operator. Okay, so let's start with the motivation of the problem, in particular with the following question. How can we define a nonlocal analog to the Monge-Ampere operator? So for those of you who are not familiar with this operator, this is essentially given by the determinant of the Hessian of some function u, okay? And in the literature, there are two nonlocal definitions that are motivated by this linear algebra property. So let's say that we have some function u that is C2 at a point x, and the Hessian of u is non-negative definite. Then this Monge-Ampere operator is given by the infimum of the trace of A transpose Hessian of u times A, where A is a positive definite matrix that has a determinant equal to 1. Okay, so in other words, the Monge-Ampere operator is given by the concave envelope of linear operators. And then just by a simple computation, we can see that we can express this as the infimum of the Laplacian of linear transformations of U, okay? So to define a nonlocal analog to this operator, Caffarelli-Charro give a very natural approach, that is to replace the Laplacian by the fractional Laplacian. Okay, and just using the integral definition of the fractional Laplacian, they give this definition, okay? So this is in the principal value sense, and the infimum is taken over this set of matrices here. Okay, so among many other things, they show that if U is convex, behaves linearly at infinity, and the fractional parameter S is between 1/2 and 1, then up to this normalizing constant, the operator converges to the classical second order Monge-Ampere operator, okay? Now, a different approach was given by Caffarelli and Silvestre, and they define a nonlocal Monge-Ampere as the infimum of integro-differential operators, okay? So here the infimum is taken over this family of kernels that is defined this way, okay? So these are non-negative functions such that the measure of these level sets is equal to the measure of the ball of radius r for any r. Okay, so here is a picture illustrating this condition. So let's say that the kernel K here is the kernel of the fractional Laplacian. Then what is this set? Well, in this case, this set is precisely the ball of radius r, right? So what this condition is saying is that we can consider any volume preserving deformations of the ball, okay? In particular, we can create these kind of things, and this is a possible level set of kernel in this family. Okay, so here we can consider any deformation in any direction as long as we preserve the volume of the ball. Okay, so by construction, you see any kernel in this family and the kernel of the fractional Laplacian have the same distribution function, right? Also, the kernels considered by Caffarelli-Charro that are given by this expression are also in this family, because you see here the level sets are just ellipsoids, and they preserve the volume of the ball given that the determinant is equal to 1. So in particular, we have that the Caffarelli-Silvestre nonlocal Monge-Ampere is less than or equal to the Caffarelli-Charro, which is less than or equal than the fractional Laplacian, okay? So even though these two operators are not equal in the nonlocal setting, when passing to the limit, they both converge to the second order Monge-Ampere operator. Okay, so with this construction in mind, our goal is to find an intermediate family of operators that is given by this expression here that are bounded by below by the Caffarelli-Silvestre nonlocal Monge-Ampere, and from above by the fractional Laplacian. And we're going to do this construction following the Caffarelli-Silvestre's approach, okay? But in this case, we will impose different geometric conditions on the kernels. Okay, so what are these geometric conditions? For example, in R3, we find this family of operators. So on one side, we have the fractional Laplacian, and we consider this to be a rigid operator in the sense that the only kernel, so we only have one kernel, okay, which is this one. And then on the other side, we have this non-local Monge-Ampere that, as I was mentioning, any kernel here is constructed by making volume-preserving deformations of balls, okay? So between not doing anything to the kernels and deforming in any direction, we find two intermediate operators. So one of them considers length-preserving deformations, let's say in one direction, for example, E1. And so what that means is that, let's say that we consider parallel lines to E1 intersected with the ball of radius r. Okay, so for example, let's look at this segment over here. So what is a length-preserving deformation? Well, for example, we can split the segment into two pieces if we want, and then shift one to the left and the other one to the right. Okay, so this is a possibility. And then a different operator is this F2 that considers area-preserving deformations. Okay, so in this case, we fix two directions, let's say E1 and E2. And then we take the plane generated by these vectors, so horizontal plane, and we slice the ball, okay? And then each slice, we make any deformation as long as we preserve the area. Okay, so these are some examples. Now, what is the precise definition? It's this one over here. So we're gonna fix some dimension greater or equal than 2, and k will be an integer greater or equal than 1 and strictly less than n, okay? And s is the fractional parameter between 1/2 and 1. So we say that a kernel k is in this family. So this depends on the parameter little k. If for all z and all radius r, we have this condition. Okay, so here now we're looking at the measure of the level sets, but just with respect to rk. Okay, so here z is fixed. And this will be equal to the measure of this ball. So this is the ball in Rn of radius r, restricted to the plane of height z. Okay, so if the plane does intersect the ball, we obtain this measure. If the plane does not intersect the ball, then the measure is equal to 0. Okay, so this is how we define our operators. The expression is the same as the Caffarelli-Silvestre non-local Monge-Ampere. But what changes here is the set where we are taking the infimum, okay, that is given by this family of kernels. So this, when U is C11, it's convex and we have this growth control, then we see that this operator is well defined. And in fact, so it's well defined point-wise. And in fact, we obtain a finite number that is non-negative, okay? And this is because by convexity, this function is going to be non-negative, right? So the graph of U will be above the tangent plane at x0. And then second property is that, so you see by the construction of this family of kernels, this is a monotone increasing family, okay? And you can think about this as, so let's say the parameter k is how many directions we consider to create those level sets, okay, to make those deformations. So the more directions that we take, okay, the more kernels we will be able to construct, okay? So in particular, when we take the infimum, this family of operators will be monotone decreasing, right? And we will have the following chain of inequalities. So the non-local Monge-Ampere will be the smaller operator because this is the largest family. The fractional Laplacian will be the largest operator because we only have one kernel, so it's the smallest family. And then our operators are in between, okay? Okay, so now that we have the definition of these operators, what can we say about them? So this is some of the questions that we've studied. So for example, first, when and where is the infimum attained? And this is interesting because you see, a priori, we don't know, because of this infimum, what the operator is doing to the function u, okay? So if the infimum is attained, we obtain a representation formula. Second, which operators do we obtain when passing to the limit? And also this is something that we do not know a priori, okay? And then third, what can we say about the regularity of this function here, okay, of k of u? So let's start with the analysis of the infimum, and I'm going to introduce some notation for convenience. We call u tilde the function, so this function over here, this is u at x naught plus x minus the tangent plane at x naught, okay? And then x, we split it into two components, y in rk and z in rm minus k. Then with this notation, we can rewrite the operator this way, okay? So the main result that gives an answer to our first question is the following. So we suppose that for all lambda or all z, the measure of these sublevel sets is finite, okay? The measure with respect to rk. Then in that case, for all z, we find a measure preserving transformation, okay, depending on z, such that the following holds. Okay, so in particular, the infimum is attained at this kernel over here. Oops, this one. So here, omega k is just the measure of the unit ball in rk. And then we will see what this measure preserving transformation, where this comes from, okay? But what is the idea of the proof of this result? So we want to minimize, we want to find a kernel here that minimizes this integral. So we know that the function u tilde and the function, the kernel k, are non-negative, right? So to minimize this integral, or this integral will be minimized when the largest values of u coincide with the smaller values of k. So in particular, this measure preserving will have to do with the way the level sets of u are rearranged, okay? And let me remind the definition of a measure preserving transformation. Let's say that we have a function defined from rk to rl. Then we say that it's measure preserving if for any measurable set E in RL, this holds, okay? So the measure of the preimage of E, so this is in RK, is equal to the measure of the set E in RL. In particular, you can think of, for example, translations or rotations are measure preserving transformations. Okay, so what are the main tools to prove this result? And these are from the theory of rearrangements. So I'm going to start with a couple of definitions in case you're not familiar with these things. So let's fix some function f that is non-negative and measurable. We define the decreasing rearrangement of f as the function f superstar, t, that is equal to the supremum over lambda's positive such that the measure of this level set is greater than t, okay? So in particular, this function is decreasing and it preserves the L1 norm of f. And similarly, we can define the increasing rearrangement this way. So one of the first ingredients that we use in the proof is this Hardy-Littlewood type inequality that says that if we have two functions f and g that are non-negative, then the integral of the product is bounded by below by the integral of the increasing rearrangement of f times the decreasing rearrangement of g, okay? So using this type of inequality, we find a lower bound for the infimum in our operators in terms of the increasing rearrangement of the function u tilde and the decreasing rearrangement of k. And then to show that the infimum is actually attained, we use this celebrated result by Riff in the 1970s that says that if the limit as t grows to infinity of the increasing rearrangement of a function f is equal to infinity, then we can recover the function f from its increasing rearrangement using this measure preserving transformation. Okay, so we use this result, Riff's theorem, for when f is the function u tilde. And this assumption here is satisfied thanks to this condition that says that the measure of the sublevel sets is finite. Okay, so this condition sorts of rules out the case where we can have like a horizontal asymptote. Okay, And you see now where this measure preserving comes from. Okay, so this comes from rearranging the function u tilde. Okay. So an important consequence is this result that says that the function fk of u at x naught is given by the fractional Laplacian of the k-symmetric increasing rearrangement of u tilde at 0. Okay, and this k-symmetric increasing rearrangement of f is given by this formula over here. So if we have a function defined in Rn, we can fix we can fix, let's say, the last n minus k variables and just rearrange with respect to the first k variables, okay? And then we can make it symmetric just by evaluating at this radial function, okay? And in particular, we want to preserve the L1 norm, so this is how we define it. Okay, and this is also known in the literature as the Steiner symmetrization. Okay, so this result is interesting because you see now we know what these operators are doing to the function u. Okay. Okay, so from the point of view of optimal transport, we can also obtain a representation formula for the operators. And this is thanks to this very classical result by Brenier and Macan around the 1990s that I stated in the form that I'm going to use it, okay? So if we have some functions f and g that are in L1, so integrable, and they are non-negative and they have the same L1 norm, then there exists a convex function psi such that the following holds. And this is for any measurable function h. And moreover, the gradient will be invertible and unique, okay? So this is known as the transfer map because in some sense it pushes forward, so the gradient pushes forward this measure to this measure, okay? So the way we're going to use this result is as follows. We fix some z that it's not that's different than 0, and we consider the functions f and g to be, so f is going to be the kernel of the fractional Laplacian, and g is going to be the kernel where the infimum of the operators is attained. Okay, remember this is the Reeves function that it's measure preserving. Okay. So in particular, these two functions are integrable because z is different than 0, and they have the same L1 norm because this is measure preserving. Okay, so by Brenier and Macan's theorem, we see that there is a unique transport map, okay, that it's given by the gradient of this convex function, such that this holds. Okay. So again, this is a new formula that we obtained from this other perspective. Okay, so moving on to the next question that I wanted to discuss is what is the limit of these operators when s goes to 1? So we show that, let's say under some very nice conditions, that the limit is equal to the sum of a k-dimensional Monge-Ampere and n minus k-dimensional Laplacian. Okay, so these operators are defined this way. Okay, so in particular here, we look at the determinant of the principal k by k matrix of the Hessian, okay, to the power 1 over k. And then this Laplacian is basically the Laplacian of u only with respect to the last n minus k variables. Okay, so very, very roughly, what is the geometric idea behind this result? Okay, going back to this picture, so here n equals 3 and k equals 2, we see that this decomposition is motivated by the fact that this operator can be understood, so at every slice, as the restriction of a Monge-Ampere operator in R2, right? So at every slice, what do? We do a measure, we do a measure preserving transformation, preserving the area, right? So that's like a Monge-Ampere in R2. And we do that at every slice, but then in the vertical direction, we are not doing anything. So that's like a rigid operator in some sense, which corresponds to the Laplacian. Okay, that's a very, very roughly the geometric idea of why we expect to obtain this sort of decomposition. Okay, so lastly, I wanted to discuss what is the regularity that we obtain for the function fk of u. And here, if we assume that u is C1, 1, okay, and S is between 1/2 and 1. So this is a well-known result that the fractional Laplacian is going to be Helder continuous with exponent 2 minus 2s. And then Caffarelli-Silvestre showed that the non-local Monge-Ampere is going to be also Helder continuous locally with exponent 1 minus s. Okay. And using similar techniques, we also show that our intermediate operators are C01 minus s locally. Okay, and a little bit the idea is that why we obtain this sort of regularity is because, as I was saying earlier, we can heuristically understand these operators as the composition of a Monge-Ampere and a fractional Laplacian. Okay, so this is the best regularity we can hope for. Okay, and so just last thing, we are currently finishing the last details in the study of this Poisson problem in the full space. Okay, so we consider an equation of this type and this condition at infinity. And here phi is a given function. It's smooth and it's strictly convex and also behaves linearly at infinity. And this sort of problem was studied by Caffarelli and Silvestre for the non-local Monge-Ampere. And using similar techniques, we showed existence of solutions via Perron's method. Okay, uniqueness follows by a standard argument using comparison principle. And then we prove solutions are C11 using some barriers. Okay, so I think, yes, that's all I wanted to talk about today. These are the main references. Thank you for your attention.